I want to start today with a question that sounds a little ridiculous, but I promise you it cuts right to the absolute core of how we build intelligent machines. If you have an aardvark and you cut it in half, do you have two aardvarks?
Please, for the record, don't cut the aardvark,
Oh, wait.
but for the sake of the thought experiment. No, you don't have two aardvarks. You have a mess.
A deceased aardvark.
Right.
Gruesome, but clear. Okay. Now, if you have a lump of butter and you cut that in half, what do you have?
You have two lumps of butter.
Exactly. And that distinction, why an aardvark sort of breaks when you divide it, but butter doesn't, is actually a massive headache for artificial intelligence.
It really is. It's the difference between things and stuff,
Mhm.
and it's just one of the absolute minefields we're navigating today.
Yeah, because today we are doing a deep dive into knowledge representation and ontological engineering.
Which I know sounds incredibly academic.
I can hear eyes glazing over already, but stick with us because this is not just theory. This is basically about how we explain the entire universe, time, space, beliefs, shopping, reality itself to a computer.
Without it having a nervous breakdown.
Right. We've spent a lot of time in previous deep dives looking at logic, the syntax, the rules of how an AI thinks. But this is about the content.
It's about what the AI actually knows.
Yeah.
How do we map the messiness of the real world into a format a machine can process?
We're trying to teach common sense to a rock, essentially.
A rock that can process logic very, very fast. But
Yeah.
yes, it has no intuition, it has no lived experience, it only knows what we explicitly tell it exists.
So let's unpack this term, ontological engineering. When I hear engineering, I think bridges. When I hear ontology, I think, I don't know, Greek guys in togas.
And you're not wrong on either count. Ontology, in the philosophical sense, is the study of what exists. What are the fundamental categories of reality? But in AI, we have to engineer those categories. We have to build a formal framework, a hierarchy, so the computer knows that a cat is a mammal, which is an animal.
Which is a physical object.
Right. And it's not just a list of words. It's a structure.
The structure that has to apply across different domains.
Exactly. We call it the upper ontology. Imagine you're building a robot that needs to repair a circuit board. But that same robot also needs to estimate labor costs for the repair.
Okay, two very different skill sets.
Very different. It needs to understand circuits and electricity, very physical, specific things. But it also has to understand time, minutes, hours. It has to understand commerce, money.
So the upper ontology tries to unify all of that into one coherent worldview.
That's the goal. But here's where it gets really interesting and, frankly, a little messy. You'd think we could just write down a master list of everything in the universe and hit save.
Yeah, just get it done.
But the source material quotes Tom Gruber, who said something fascinating. He said, every ontology is a treaty, a social agreement.
A treaty, that implies conflict, or at least a negotiation.
That is the crucial insight. It implies that people define things differently based on what they want to do.
Can you give me a concrete example of that? Where does the conflict happen?
Think about a tomato. If you're a shipping company, a tomato is a product. It has a weight, dimensions, a SKU number.
It's just a box to be moved.
It's just a box to be moved. But if you're a chef, that tomato is an ingredient. It has flavor profiles, acidity, texture.
And if you're a botanist?
It's a fruit, specifically a berry.
So getting the shipping software, the restaurant inventory software, and the scientific database to agree on what a tomato is, that's the treaty.
Exactly. And getting everyone to sign that universal treaty is incredibly hard. It's basically specialized politics for data. That's why most AI uses special purpose engineering, not one giant shared ontology.
But the dream is still that general framework, the upper ontology.
That's the dream.
So let's walk through this hierarchy a bit. At the very top, you have anything.
Right. The set of all things.
And then it splits. You get abstract objects like numbers and sets, and generalized events.
And under generalized events, you find physical objects.
Wait, hold on. That seems weird. I think most people would categorize a table or a human as a thing, not an event. Why is a physical object a type of event?
That's a major perspective shift. You have to think of a physical object not as a static statue, but as a chunk of space-time.
A chunk of space-time.
The United States, for example, can be thought of as an event that started in 1776 and is, well, still happening.
The United States is an event. I like that. It's a work in progress.
Precisely. Even you or I, we are events. We occupy a specific volume of space for a specific duration of time.
And this hierarchy lets us use inheritance, right? Just like in object-oriented programming.
Exactly. Like in Java, if you define a generic window, You can then make a specific spreadsheet window that inherits all the basic window traits.
So if we define physical object correctly in the upper ontology, saying it has mass, it responds to gravity.
Then you don't have to redefine gravity every time you invent a new toaster. The toaster inherits gravity compliance from the parent category.
But the real world is so much messier than a spreadsheet. We've talked about the Wumpus world in previous deep dives, that simple game where the AI hunts a monster.
Right, the Wumpus world is what we call a toy domain. Time there is just discrete steps. You move, then I move. Nothing changes unless you touch it.
But in the real world, things happen simultaneously. While you're brushing your teeth, the bathtub is filling up.
And if you don't pay attention, the bathtub overflows, which is a disaster for an AI that thinks the world stops moving while it thinks. We need an ontology that handles that complexity.
Which brings us right back to my aardvark and the butter. This is that distinction between count nouns and mass nouns.
Or as the source puts it, things and stuff.
And this is one of those things humans just get, instinctively. But we have to teach the AI explicitly.
Right. An aardvark is a thing, a discrete object. It has what we call extrinsic properties, like its shape, its weight. If you cut it in half, you lose those properties, you destroy the thing.
But the butter?
Butter is stuff. It has intrinsic properties, density, color, flavor. If you cut a lump of butter in half, the piece in your left hand has the exact same density and flavor as the piece in your right hand.
So stuff retains its identity when you divide it. Things do not.
Correct. And we even talk about them differently. You can say an aardvark. You can't really say a butter.
I'll have a butter, please. Yeah.
Sounds wrong.
Unless you're at a very pretentious restaurant.
But this gets even trickier when we try to define natural things. I mean, strict definitions work for math. A triangle is a polygon with 3 sides, period.
If it has 4 sides, it's not a triangle. That's a logical fact.
But try explaining a tomato to a computer with that kind of strict logic.
This is the tomato problem, or the issue of natural kinds. If you tell the AI a tomato is a red, round object, and then it sees a yellow heirloom tomato, it might think it's a grenade. Or a lemon.
Or very sick apple, yeah. Because in reality, categories have fuzzy boundaries. Tomatoes are usually red, but not always. They're usually round, but sometimes bumpy.
So how do we code for that? We can't list every single tomato in existence.
The solution is really interesting. We move away from strict definitions to what the text calls typical tomatoes. We write a rule that says, typical tomatoes are red and round.
So you're building in the idea of a default case.
Exactly. It lets the AI reason about the default case while explicitly acknowledging that exceptions exist.
It's like what Wittgenstein said about games. There's no single definition that fits chess, tag, solitaire, and, dodgeball. They just share a family resemblance.
That's the perfect analogy. We have to teach the AI to look for family resemblances rather than strict mathematical laws for everything. If it looks like a duck and quacks like a duck, it's typically a duck.
But you leave room for the possibility that it's a mechanical decoy.
You have to.
Speaking of laws, let's talk about money. The source makes a really subtle distinction about measurements. It says that $1 is not the same thing as a dollar bill.
Right. This is about abstracting measures. $1 is a measure object. It's a concept. A dollar bill is it's a dirty piece of paper.
A physical object. You can have $2 bills, but there's only one abstract concept of $1. Why does an AI need to know that?
Because it leads to qualitative physics. We don't always need precise numbers to function. If I tell you exercise A is harder than exercise B, and harder exercises result in lower scores,
then you know your score on A will be lower than on B without ever knowing the numbers.
Exactly. You don't need to solve a differential equation to know that if you drop a rock on your foot, it'll hurt. You just need rock is heavy and impact causes pain. This qualitative reasoning is a huge shortcut for AI.
Okay, let's move to one of the hardest things to pin down. Time. We said the simple step-by-step time of the Wumpus world doesn't work. So what's the upgrade?
We have to upgrade from situation calculus to event calculus.
Situation calculus sounds like what I do when I'm assessing a threat in a bar. What's the situation?
In AI terms, it's kind of like that. Situation calculus treats the world as a series of snapshots. Snap, the tub is empty. Snap, the tub is full. It misses the process of filling.
It's a stop-motion movie where you miss the movement between frames.
Perfectly put. And event calculus introduces fluence.
Fluence, like being fluent in a language.
No, think fluid. A fluent is a fact that can change over time. Like at Schenker Berkeley, that's a fluent. It might be true at noon and false at 1 p.m.
So event calculus tracks how those facts change.
Right. It uses points in time and intervals. It lets us say, this fact became true at time t1 and stopped being true at time t2.
And this lets us handle those liquid events we touched on earlier. I love this term. It connects back to the butter, doesn't it?
It connects perfectly. Remember how stuff like butter acts when you divide it? A smaller piece is still butter. Well, liquid events or processes are the temporal equivalent of butter.
Time.
I knew you were going to say that. But yes, take the concept of flying. If Shankar flies from San Francisco to D.C., that is a discrete event. Start, finish.
But the process of flying, if you take a 20-minute slice of that trip, he is still flying.
Just like if you take a slice of butter, it's still butter.
I see. So flying is a liquid event category. A flight is a discrete event.
And that distinction is vital if an AI is trying to schedule things, because schedules are all about relationships.
I can't meet you during my flight.
Right. Which brings in the Allen interval algebra. It sounds complex, but it's just a vocabulary for how time chunks relate. Events can meet, like the reign of Elizabeth II met the reign of George VI. They touched, but didn't overlap.
Or they can overlap, like the reign of Elvis overlapping with the 1950s.
Precisely. It gives the AI a way to reason. If I'm supposed to be in a meeting and the meeting overlaps with my dentist appointment, I have a conflict. It's obvious to us, but you have to code that logic from scratch.
Okay, so we have stuff, we have time, now we need to get inside the head. Mental events, beliefs.
This is critical for any social interaction. It's not enough for an AI to know facts. It needs to know what other people know.
Or what they think they know.
Right. If I ask you, is your mother sitting down right now? You probably don't know.
I have no idea.
But you know that she knows.
Right. I can call her and ask.
The AI needs to be able to model that. It needs to handle what are called propositional attitudes. Things like believes, knows, wants.
But this leads to the Superman problem. And I love this because it sounds like a comic book plot hole, but it's actually a logic bug.
It's a classic issue called referential opacity.
Yeah.
So here's the setup. Lois Lane knows that Superman can fly.
Correct. That's a true statement.
And we, the audience, know that Superman is Clark Kent.
Also correct.
Now, in standard logic, there's a rule called referential transparency. It means if X, Y, you can swap X for Y anytime. So, if Superman is Clark and Lois knows Superman can fly.
Then standard logic would say Lois knows Clark Kent can fly.
Exactly.
But she doesn't. That ruins the whole movie. She treats them as two totally different people.
And standard logic fails here because it doesn't respect the mental state of Lois Lane. It assumes her knowledge is transparent to the facts of the universe.
So how do we fix this? How do we keep the plot twist alive for the AI?
We use something called possible worlds and modal logic. Instead of just one world, the real one, we imagine a set of accessible worlds that are consistent with Lois's knowledge.
Accessible worlds. So we're modeling her imagination.
In a way.
Huh.
In all the worlds that Lois considers possible, Superman can fly. But in some of those worlds, Superman and Clark Kent are two different people. So in her belief worlds, Clark cannot fly.
The AI can say, in the real world, Clark can fly. But in the set of worlds inside Lois's head, he can't.
Yes. It models her perspective as a separate logical space. This is essential for negotiation or deception.
That is incredibly cool. But doesn't this assume the AI or the agent it's modeling is a perfect thinker?
That is the problem of logical omniscience. Modal logic usually assumes that if you know a set of facts, you know every single logical consequence of those facts.
Which is physically impossible.
Right. My brain has limits. Even a supercomputer has limits. Real agents have limited rationality. We run out of time, we run out of memory. So we often pretend agents are omniscient just to make the math work while acknowledging it's an idealization.
Fair enough. Okay, I want to pivot to something that feels very human. Jumping to conclusions.
Default reasoning.
Logic is usually about absolute truths. If A implies B and we have A, we have B forever. But in real life, we assume things. If I say, Tweety is a bird, you assume Tweety flies.
Right. That's a safe bet. But what if I then tell you Tweety is a penguin?
Then I take it back. Tweety doesn't fly.
This is called nonmonotonicity. It's a $10 word for a simple concept. In standard or monotonic logic, adding new facts just adds to your pile of truths. It never subtracts.
But in common sense, adding new information can force us to retract old conclusions. It's like the system needs a backspace key.
Exactly. We see this beautifully in the Nixon diamond.
A classic example. Lay it out for us.
Okay, so Richard Nixon was a Quaker. Typically, Quakers are pacifists. So, default rule 1 suggests Nixon is a pacifist.
Nixon was also a Republican.
And typically, Republicans, especially in that era, were not pacifists. Default rule 2 suggests Nixon is not a pacifist.
So you have two default rules clashing, a diamond shape in the logic graph. One says yes, one says no. What does the AI do?
Well, it has to decide. Does it refuse to conclude anything? Does it have a priority system? This is where we use techniques like circumscription.
Circumscribing.
It basically means we assume abnormal things are as rare as possible. We assume Nixon is a normal Quaker unless forced to believe otherwise. But since he's also a Republican, the logic gets jammed.
So you might need something else.
You might need a truth maintenance system.
A truth maintenance system? That sounds Orwellian.
It sounds sinister, but it's actually just good housekeeping. It's a system that tracks the justification for every belief. If I believed the car would start because I believed the battery was good.
And then you find out the battery is dead.
The truth maintenance system says, okay, the premise is gone, therefore the conclusion car will start must be deleted. And anything inferred from that belief, like I will get to work on time, also gets deleted.
That's like a digital janitor for your belief.
Or a historian. It keeps the timeline consistent so you don't end up with a worldview that contradicts itself.
So we've built this massive toolkit, ontologies, fluence, modal logic, default reasoning. What do we actually do with it? The source brings this all together with internet shopping.
It's the perfect test case because the internet is a mess. The World Wide Web is not a neat grid like the Wumpus world.
No, it's a jungle of HTML.
Exactly. Malformed HTML, missing tags, text, hidden inside images. An AI agent have to look at a string of characters and realize, oh, this is a price. This is a product description.
And the language is ambiguous. If I search for notebooks, do I want a laptop or a stack of paper?
Right. And if I search for CDs, do I want music or a certificate of deposit? The agent has to handle synonyms, realizing laptop and notebook computer are the same category.
And the text mentions wrappers. These aren't sandwich wrappers.
No, they're procedural attachments. Little programs that scrape the messy text to find the gold, the price, the CPU speed, the shipping cost.
And once it has that data, it has to compare offers. Let's say offer A is $300 and fast shipping. Offer B is $400 and slow.
Offer A wins. It dominates. Offer B, easy logical choice.
But what if offer C is $200 but really slow?
Now logic fails. We have a trade-off. Is the speed worth the extra $100?
That depends on the user.
Exactly. Now we need utility theory user preferences. But notice, the knowledge representation part, the ontology, is what allowed the agent to even understand that price and speed are things that can be compared in the first place.
Without the ontology, it's just looking at meaningless numbers.
That's it. So what this all means is that knowing something is incredibly complex. We started with a map of the universe, and we realized the world is made of things and stuff, events and processes.
We saw that mental states complicate the picture because people can be wrong.
And we saw that we need to make default assumptions to function, even if we have to correct them later. And all of that entire philosophical and logical heavy lifting is happening just so a bot can find you a cheap laptop on Amazon.
It really makes you appreciate the human brain, doesn't it? We do this ontological engineering every millisecond without even trying. We know a tomato is a fruit vegetable thing. We know Lois Lane is wrong about Clark. We know Nixon was complicated.
We do. And it raises a final, maybe provocative thought.
What's that?
The single ontology. The source material notes that the project of building one single perfect description of the universe has largely been abandoned. It's just too hard. We use smaller, linked ontologies instead.
So we've given up on the treaty.
In a way. And you have to ask yourself, if we humans can't agree on a single treaty for how to describe the world, if we can't even agree on what a tomato is, can an AI ever truly understand the world the way we do?
Or will it always just be translating between different fragmented views of reality, never quite seeing the whole picture?
That is something to mull over the next time you're cutting a lump of butter.
Or an aardvark. Please don't cut the aardvark.
Stick to the butter.
Thanks for listening to this deep dive. We'll see you next time.